Hey class, this is Brother Schneff. This is a example problem for section 1.2, which deals with scalars and vectors, vector operations, and vector addition of forces. I am intending that these example problems are just supplemental to what's already provided in the prepare section for each unit. So I'm assuming that you've already gone through the lecture videos, gone through the available examples, and if you need additional um, examples or help understanding them, then you come and watch these videos. And I will, in these videos, I'm going to attempt to demonstrate the principles in the unit and also good formatting. Um, so hopefully you find these helpful. I'll try to do them, have example problems for basically every subunit this semester. Um, so hopefully these are something that you can go to and get some help with and understand things a little bit better. So in unit 1.2, we're talking about scalars and vectors. And if you aren't, maybe haven't taken a physics class yet, vectors might be a little bit confusing, but you're going to get to know them very well during the course of this class. As they explain in the lecture video, scalars are just numbers. They're just a magnitude, they're a value. And the difference between a scalar and a vector is that a vector has a direction component. So and we will typically represent them using arrows, representing that. Not only does this thing have a certain magnitude, but it's going in a certain direction, whether that's in 2D, like we do in this in Unit 1, or 3D, as we'll get into in Unit 2. And vectors can be added together. We'll be talking about all sorts of kinds of vectors, force vectors, position vectors. In this particular example, this is coming out of the book. This is I have the 13th edition of the book. This is problem 2.29 in that. And it's, in this case, the problem is being represented as this pair of tugboats. So that's the problem that I'm going off of. That's the representation. So I've redrawn it here. And part of the good formatting, so one of the key things we look for is that there is a given section where you clearly state what information is given. You include any diagrams that may be included or pertinent. And then there's a find section where you just state out what are you actually trying to find. So in this problem, we have two vectors. There's a force A and a force B. Force A has a magnitude 2 kilonewtons and is 30 degrees from the positive x-axis. And force B has a magnitude of 3 kilonewtons and is 45 degrees in the negative direction from the positive x-axis. And what we're trying to find is the magnitude of the resultant force and direction measured from the positive x-axis. So basically, we're just going to add these two vectors together, find out how big is the resulting force that we get, and what direction is it going in. There's a couple different ways we could go about this. You may see cases where people will do tip to tail addition, where you add the vectors together, and then you can write something like this, where you, what's going on with my marker? Oh no, my marker's dying. Where you'd have, that'd be force A, and that's force B. You stick them tip to tail, and then this would be your resultant. I find that, if you're very graphically minded, that might help you understand it. Maybe it's helpful for the first few times just to kind of see how that works and how it makes sense. I find it difficult, though, once the problems get more complex, and I prefer just using what we call Cartesian coordinates, or basically you break each vector into X and Y components. So that's how I'm going to approach this, is by breaking it into Cartesian components and adding the separate components together. So I'm going to start by just defining. Right now we have a magnitude for each vector. We have a direction, but I need to convert that then into Cartesian coordinates, or otherwise an X and a Y component for each of these forces. So I know that eventually what I'm going to get to is that my resultant force is equal to force A plus force B. That's my equation that I'm eventually going to get to. I'm just going to call this equation 1. I kind of like this method of numbering key information so that I keep track of it later and make it clear when I'm using what information. You don't strictly have to, but it's just something that I like to do. So this is my first equation, and I'm going to then figure out what FA is equal to. So FA, the x component of F is going to be the magnitude of the vector 2. And then because we have an angle, we can use our trig identities, cosines and sines. And so in this case, I would use the cosine, because the cosine will get me the adjacent length. Basically, it's going to give me the ratio of the overall length of the vector to the adjacent length of the vector, right? Because cosine is the opposite over the hypotenuse. It's a ratio. It's saying if this hypotenuse is a certain length, then the adjacent length will be some percentage of that length. So the cosine will always be 1 or less between 0 and 1. So in this case, it's going to be cosine of 30 will get me that adjacent length, which in this case, the adjacent length happens to be in the x direction. And I'm going to use this little I hat to indicate that that is in the x direction. And it's positive, right? This vector is pointing in the positive x direction. And then I'm going to add, or I'm going to figure out the y. So the y component is going to be some fraction of the overall length of the vector, so 2. And in this case, that fraction is represented by sine of the angle, right? Sine is the relationship between the opposite length of a triangle and its hypotenuse. So I'm going to do 2 sine 30. And if I just evaluate those numbers, I get FA is equal to, actually, I'm gonna just leave it like this for now. This is my second main equation. And then I'm going to do the same thing for FB. So FB, so I have 3 is my magnitude, and cosine 45 will give me that relationship between the adjacent length, right? If I were to make this a little right triangle, the adjacent length, which in this case is the x direction, so cosine 45. And that's going in the positive direction. In this case, it's actually pointing downward. So when we are talking about the y part of it, it's going to be a negative. I'm going to end up with a negative y. I just want to say minus 3 sine 45. Okay. That's the third equation. So I'm going to plug in equation 2 and 3 into 1. So I'm just going to indicate that. I'm going to say 2 and 3 into 1. And again, you don't have to use this numbering. I just like to. It helps me keep things organized. And what I end up with is that my resultant vector is going to be, I'm going to add, I can add the x's together and I can add the y's together. So I'm going to get 2 cosine 30 plus 3 cosine 45. That's the x component, plus 2 sine 30 minus 3 sine 45. And that's the y component. And then when I evaluate those numbers, I get that my resultant force vector is 3.85 I and minus 1.12 J. So it's going in the positive x direction and it has going a little bit in the negative y direction. So that's the vector. The answer, it didn't want me to actually find the vector though, it wants me to find the magnitude and the direction. So to get the magnitude and the direction from this, right? So basically what we found is a vector that, so I can represent this as sort of a, well, let me draw the right direction. All right, so this is what our vector would sort of look like. It has a positive x component and a positive y component. And I basically end up with a little bit of a right triangle. So if I want to find the hypotenuse of this right triangle, the overall magnitude, I can just use our good old Pythagorean theorem and take the square root of 3.85 squared plus 1.12 squared. right? Or two lengths, and I'll end up with the overall magnitude of that vector. So when I do that, I'm say magnitude of the resultant force is equal to the square root of 3.85 squared plus minus 1.12 squared. The minus sign is going to go away because we're squaring it, and what I end up with is 4.01 kilonewtons. So another thing with a standard is on your final answer, you need to have units and you need to indicate it. Typically, I prefer a big arrow that goes out to your margin like that, or a really obvious box, but you have to indicate your answer in some form or fashion, or else you will get docked points. So that's one final answer. So I got the magnitude. Now we need to find the direction. To find the direction, we can go back to our trig laws. So basically, we want this angle. And there's a couple of laws we have, right? Cosine, sine, tangent. Typically, I found the easiest one to use is tangent, right? So tangent is the opposite length over the adjacent length, right? So if we were to write that, I could say the tangent of that angle equals the opposite length, which is minus 1.12, divided by the adjacent length, which is our x component, 3.85. And then I would just take this value and take the inverse tangent. So I'm going to just pop up over here, kind of cheating, but I'm running out of space. So I'd say the inverse, or the theta equals the inverse tangent of these values, so minus 1.12 divided by 3.85. And when I evaluate that, I end up getting that theta equals negative 16.22 degrees. And that would be my other final answer. So that's how you can go about solving any given 2D force addition type problem. There you'll see a lot of different variations in this sort of problem in the homework, but that's the general idea of it. If you aren't super familiar with your trig laws, or your basic trig identities, I should say, your sine, what cosine is, what sine is, what tangent is, you'll get lots of practice with it. And if you need help, reach out to me or the tutor, and we'll be happy to give you a refresher. I know for some of you, it may have been several years since you've had to use those. I know when I took this class for the first time, these were things from 3 or 4 years ago, and it was took me a little bit of time to remember what these things meant. But I'm happy to refresh those with you anytime. And hopefully this is helpful for you in solving the problems related to Unit 1.2.